All right, so we have, we're trying to solve for x here, which is going to be the shift for, right, x is the shift for this problem here. We have this chemical reaction, we have the initial, we're creating an ice box, the initial concentrations provided above. The change based on the shift, we know it has to shift to the right because we have no B to start with. You can also compare the Q and the K if you want to. And so we have the equilibrium concentrations. We put the equilibrium concentrations into the equilibrium expression here. And now we're just trying to solve for x. Now the problem is we have this quadratic here. Now we can solve quadratics, that's not terrible, but it's definitely much more time consuming. And if there's an easier way, then we want to be aware of that. Now 3.5 times 10 to the minus 16. This is the resulting expression, result of this expression at equilibrium. So the shift is not going to be, is going to be near the order of magnitude of this 3.5 times 10 to the minus 16, right? We started off with 0.2 of A, and the relative relationship, again, the concentration of B over A squared is going to be 3.5 times 10 to the minus 16, which is a very, very small number. So there's not going to be very much B formed. So because of that, X here, which actually will represent the amount of B that there is as well, you can see, right, is going to be a very small number. And so because of that, we can actually take this 0.2 and disregard the minus 2x, because it's not going to be a very large number. And so we can say that that 0.2 minus 2x is actually going to be about 0.2 because the shift is so very small. Therefore, it becomes easier to solve the problem. So essentially what we did is we dropped the shift of the 2x. And that makes things much easier to solve because now we just have 0.2 down here, not 0.2 minus 2x squared, 0.2 squared, and we can solve for x. All right, so 1.4 times 10 to the minus 17 is what the concentration of B is. It's what the shift is going to be. And we can, if we want to, we can say, is 1.4 times 10 to the minus 17 divided by 0.2 less than 0.05, right? So essentially we're comparing the amount of this shift to this value. Another thing you can do is just put 0.2 and subtract, not 1.4 times 10 minus 17 because we multiply by 2, but 2.8 times 10 to the minus 17. And the answer will be 0.199999999, which is essentially 0.2. Okay? All right. So we're showing that we can drop this shift, this change, from our initial concentrations if the value is very large and the shift is very small. And we'll get some experience with how we can know when we can do that.
Yeah, because I can't tell how you knew that it was okay to do.
Well, there's a couple of things that we have that we'll be able to determine. The one thing that we could see here is that because this value was very, very small, and this value is very large relative to this value, the shift was going to be very small. We also solved for the shift and saw that it was 1.4 times 10 to the minus 17. Now, this is an approximation because this we dropped that term there, right? However, because it's so small, it's not going to be changing the 0.2 very much, and so it ends up being a close enough value for us. All right, so let's try this one. Are you ready to give it a shot by yourself, Fred?
I could try.
All right, why don't you folks at home try to solve this problem, and if you can, then that's great. If not, give it a try at least. Push pause, give it a try, and then we'll work on it together. All right. Did you try?
Yeah, I tried.
What'd you get?
Well, let's walk through it, right?
Yeah.
So HC2H3O2.
HC2H3O2.
plus H2O, yielding H3O plus the acetate ion, C2H3O2 minus.
Okay, very good. So there's our chemical reaction.
We start with 0.3 molar of the acetic acid, the initial stuff.
All right, so we go through and we identify our initials. 0.3 molar. How much water?
Well, that's a liquid. We don't care. That's not in the expression.
Okay. How much of this stuff do we have?
It doesn't say we have any of that.
So 0 and 0 of this then, right?
Right.
Okay. Now what will the final concentration of this be?
Well, the shift. We have to find the shift first, the change.
Very good.
And we're going to lose reactants and gain products. And it's 1 to 1 to 1 to 1, the stoichiometry, right?
Yeah.
So just minus X there for the reactants.
And this one we don't care about.
Plus X for the products.
Okay. Now, how did you know that?
Well, I just knew because they didn't tell us that there was any products. So there has to be a shift to the right.
That's right. Now, what about the equilibrium concentration?
Well, it's just 0.3 minus X. And then on the right, just X and X.
All right, so essentially we're adding those initial and the change together, right?
Yeah.
All right, now what do we do?
Well, we have our equilibrium expression. The equilibrium expression is going to be the products over the reactants. So the acetate ion and the hydronium ion over the acetic acid. And that equals 1.8 times 10 to the minus 5. Okay, now you can put in those equilibrium concentrations, which are
See if we can get it all in here. Get this up a little bit higher.
equilibrium concentrations are for the acetate ion X, for hydronium ion X.
Okay, X times X over
0.3 minus X.
0.3 minus X.
That equals 1.8 times 10 to the minus 5.
Okay, now what?
Now you, well, if you keep going here, you're going to get a quadratic, right?
Yeah, we will get a quadratic. We'll get X squared over here, and we'll get 0.3 times that and X times that, right?
So that makes it a little more difficult. Does it help if we drop a term?
It does. Can we drop that X?
Well, we could try it. I'm not sure how you know exactly.
Well, see, look at the shift here, or not the shift, but the equilibrium, 1.8 times 10 to the minus 5th. That's not the shift, that's the equilibrium, but that's going to be in the ballpark of the shift. So if we start with 0.3 and subtract the whole equilibrium, which is not what we're going to be doing, but if we did that, we wouldn't change 0.3. This is a very small number. The actual resulting value would still be, to one significant figure, still be 0.3, okay? So that's an indication that we can drop that. And once we drop that, that gets rid of that and simplifies our quadratic, right? So then we just take 1.8 times 10 to the minus 5 times 0.3. 1.8 times 10 to the minus 5 times 0.3. There we go. And 5.4 times 10 to the minus 6. And that is going to equal, so we drop this, multiply that by that, and that equals X squared. So now I take the square root of it, and I get 0.0023. X equals 0.0023. Now, is that the equilibrium concentrations?
What will be the equilibrium concentration of the acetate ion? And it's 0.002, so it's got to be B.
Okay, so X is the equilibrium concentration of the acetate ion, right, in our icebox. Okay, very good. All right, now we do have a solver in our calculator. If you ever want to actually, so if for example, the shift is close to the concentration, then we can't drop that that term. Can't drop that term. We have to use a solver, or we can use the quadratic equation formula if you want to do that. But I want to introduce to you the solver in your calculator, or reintroduce to you. You probably have learned about it a couple times already in your math classes. But we go to math. Let me pull this up out of the way. Get this the whole screen here. We go to math. We go to the very bottom of the list here, which is, or you can just go to the top and go backwards. Solver, enter, and then we type in the equation here. So let me bring this up. What is our equation that we're trying to, whoops. 4x squared plus 4.5 minus 0.675. So I type that in up here. I'm going to insert right there. 4x squared plus 4.5, insert 4.5 x, this is supposed to be x, so here's where we get the x right there. Minus, instead of minus 1.675. All right. So I push enter there, and what it usually does here is it will display my equation and ask for me to choose a guess. It's where I think the value is. And 2 is a fine guess. I really don't know where the value would be, I guess. Haven't really thought about it much. It's probably less than that. But that is a number that it puts in for x and tries to find a minimum. And if that number doesn't work, it changes the x, changes it to 3. If that doesn't work, it changes. If it's farther away, it changes it the other way, it changes it to 1. And it keeps doing that until it finds an answer. And so to get it to solve now, I need to get that green solve button there. I go to alpha solve, like that, and it'll get me an answer of 0.134. All right, so this is a quadratic. There are 2 roots. To find the other root, you can change the x here and get closer to where you think the other root is. You can also adjust your bounds here by saying, I don't want it to be bound from, well, there you go. I can change the bounds here to exclude the region where the 1 root already is. But YouTube, lots of different videos on YouTube that'll show you how to do this. Okay, good job.